everybody, video number 2 for today. This is a bit of a recap on where we were before spring break, looking at fusion reactions as well as how they apply to stars. It's always nice to start a unit with something that's familiar, that's something that ties to what we did last time, even if last time was quite a while ago and feels like a lifetime ago. So this is where we were. This is the same set of slides more or less. I think my writing is gone, but that's okay. We were looking at fusion reactions as the joining of two lighter nuclei to form one larger one. We looked a lot at the benefits and drawbacks of nuclear fusion, mainly looking at it in terms of its feasibility as a source of electrical energy. So this is moving away from that, but it's still the same kind of idea around nuclear fusion and how that process happens and why it happens. We also looked at the fusion bomb, such as it were, how fusion is a process that requires such high temperature and high energy to get going that a fusion bomb, a hydrogen bomb, actually has a fission reaction up at the top as its trigger. So the fission, usually of uranium, releases so much energy, and then that energy is enough to kickstart fusion in the bottom material. It's labeled as red here, but this is a black and white diagram, so it's definitely not red. These were first tested in the United States in 1952, and the other piece that we talked about before spring break was to do with some of the geopolitical aspects of science in that time period during the Cold War, and how scientists got very nationalistic. Why would I tell you about the research I'm doing if you were going to use it to harm me? The other thing we looked at was the process of fusing hydrogen into helium in the sun. Where we saw that was on the lesson about mass defects. There was this sheet that had a few calculations to calculate the energy released in different fission and fusion reactions, as well as just alpha decay was the first one there. All right, so this is where we were in calculating mass defects from different reactions. The one I want to focus on at the moment was question 3 about nuclear fusion in the sun producing helium-4 from hydrogen. So it took 3 steps. It wrote them in nuclear equations and gave you the image here. First step, we take 2 hydrogen nuclei. They fuse together and undergo beta plus decay to release a positron and a neutrino and energy. A second proton hits that hydrogen 2 nucleus to form helium-3. It releases gamma rays. And then 2 helium-3 nuclei. So there's a whole second set of steps 1 and 2. 2 helium-3 nuclei join together. They form helium-4, and the extra 2 protons are ejected. We calculated the total energy released using mass defects. So for each one of these 3 equations, what was the mass before, what was the mass after, how much was missing, convert that to kilograms, and then use E equals mc squared to calculate the amount of energy released. So because we needed 2 sets of step 1 and 2, we needed twice our answer for the first step, twice our answer for the second step, and then just one of our answer for the third step, added together to get the amount of energy released by just one set of these steps happening. The next question, or the next part of the question rather, had you look at then the power output of the sun. Power output of the sun is approximately 4 by 10 to the 26 watts. The more exact number is 3.84 by 10 to the 26, or approximately 4 by 10 to the 26 joules per second. So that gets a special vocabulary term in astronomy. That's something we call the luminosity of the sun. It really just means the power output, or how much energy per second is being released. How we experience that is brightness. If something has a very high luminosity, it means that there's a lot of energy being released. And so to us, that star would seem brighter than something with a lower luminosity. There is, of course, the condition of distance. If something is very, very bright and far away, we still see it as dim, but we'll get into that in a later lesson. The last bit of the question asked you to then calculate, given the fact that 4 hydrogen atoms are used up in this process, figure out how many kilograms of hydrogen are fused into helium every second. So use the amount of energy you calculated, the amount of energy per second, to then work backwards to get how many kilograms of hydrogen are fused into helium every second. So that's a really big number. 6 by 10 to the 11 kilograms is a number that is unfathomably big, but thankfully so is the mass of the sun. You'll notice in this that this is almost a reverse of the chain reactions that we were looking at. When we were looking at the fission of uranium, we had neutrons that were released in the end that caused a chain reaction because they went and hit more uranium nuclei to release more neutrons to hit more uranium nuclei. And this is almost the opposite. We start with 6 hydrogen nuclei. There's 2 at the beginning on each branch here, and then a third one on each side comes into play along the way. So it takes 6 hydrogen nuclei to do this process. Those are our inputs. Our output here is 1 nucleus of helium-4 and 2 of extra protons. So over time it's used up. Our net input here is 4 protons to create this. Where those 2 neutrons come from is because of the beta decay happening along the way. And so over time, the sun is going to use up its supply of hydrogen. So in this, we call this the proton-proton chain. Oh, my pen is not, there we go. There we go. Sorry, you have to bear with me as I'm learning how to do this all. This is a new experience for all of us. This is called the proton-proton chain because it begins, each section of it begins with the 2 protons and results in a set of reactions to form helium. So I mentioned before, we have 1, 2, 3, 4, 5, 6. There's the other one. Hydrogen nuclei, and in the end, we're getting 1 helium nuclei, and then these 2 will go off. So it's kind of the opposite of a chain reaction. When we were looking at uranium fission, we were noticing that those extra neutrons could go on and hit something else, and they could cause the next uranium nuclei to become unstable and to react. This process is the opposite because it uses up the hydrogen over time. We start with 6, we release 2 in the end, and over time the hydrogen in the sun is going to get used up. Along the way, however, this is producing immense amounts of energy like we saw when we did those calculations. At every step, notice all the places where energy is released. All of these products that are being released, so here's a positron, here's another positron, the neutrinos, gamma rays, anything that's a real product like these guys is going to be released with some amount of kinetic energy. So there's energy being taken away from this reaction, being carried away. Gamma rays basically are energy. They weren't matter. They were the kind that don't result in transmutation. So we see all of this energy as light. And over time, this will use up. So this is referred to as the luminosity. A little bit about astronomy nomenclature. You're going to see a lot of symbols that have that little circle with a dot subscript. This just means sun. So I'm labeling it. I'm talking about the luminosity of the sun. In another slide, I'm going to talk about the temperature of the sun. Or maybe I would be talking somewhere else about the mass of the sun. Whatever quantity it is, I use that little circle with the dot in the center to label it as the sun. So in our case here, the luminosity of the sun, if I do a slightly more exact value than from that calculation sheet, is about 3.84 by 10 to the 26 watts. Immense, beyond immense. Some of the factors that affect the luminosity of any star, not just our star. First one that affects it is the temperature. I'm sure you can imagine that if something has a higher temperature, it implies its luminosity will be higher. Kind of makes sense. Temperature is kinetic energy. If something has a higher temperature, there's more movement happening, there's more energy being released. In terms of the size, which is not the mass, this would be like the radius. I'm sure you can also convince yourself that it makes sense that if the size is larger, so is the luminosity. And finally, if the mass is larger, then the luminosity is larger as well. Large stars, and by large I mean massive. I will correct myself. Massive stars are, they're kind of an interesting breed. They're very fast and furious. They have high mass, which means there's a lot of hydrogen to work with, but a high luminosity means they're burning a lot of that hydrogen all at once. They're releasing a lot of energy all at once. So they actually don't live as long. They burn through their supply very, very quickly. They're fast, they're furious, and then they burn out. So their lifespan is actually a lot shorter than something that is smaller and less hot. I'm going to pause this here just so each one of these doesn't take too long to upload. I'll see if this works for me, and I will see you on the next video.